Hello and welcome to this tutorial. I was just going to go ahead and go over the recent little weekend project script that I had written, which is on, it's a finite subdivision rule script, namely on Pentagonal subdivision. And if you aren't exactly sure what that means, it's if we take some sort of polygon, for instance, and want to subdivide that into smaller components or geometries, we can find or create different types of rules to do that. Probably the most classic example that you might be able to think of or that you may have seen in these terms is subdivision of the square, where we subdivide the square into many or different types of squares. Maybe we subdivide it like given at the half of any line segment on that square, we divide that in half. We choose vertices that would correspond to the midpoint of each line segment on the square, and subdividing that further until we form something like the grid of a graph paper is a common example. Well, in the case of pentagonal subdivision, and this is shown in the next slide here, we can see that we have a unique rule relative to the example that I cited before, and that we might be choosing, say, between two vertices, a midpoint subdivision, shown, for instance, in the upper left corner of the, or upper left region of this pentagon. We have one vertex, and that would be at the given midpoint between these two particular vertices on the pentagon, and we can see that there's a symmetric rule that's applied for each line segment running on the pentagon, at least the outer polygon that's shown there. So we go, for instance, for any two vertex pairs that form a line segment on the pentagon. We see there's a midpoint subdivision that's given, and this is done on all such line segments on the outer polygon. If we actually look at this further in the diagram, and this is again just given at one level of subdivision, so as to kind of visually simplify the process of what is going on in terms of just one subdivision level on the polygon. So we see that we have all of these midpoints that are created on the outer polygon, and that they have what I call spokes that radiate. These are line segments that radiate as given perpendicular line segments from that existing line segment that is shown on the outer polygon. So this line segment that we can think of as almost like spokes on a bicycle wheel, they radiate inward to a given region, and then we have, you'll notice it's an interior polygon that's yet another pentagon at the center, except it looks like it's almost kind of rotated 90 or 180 degrees in the opposite, so that it's literally kind of upside down. And these would form the basis of, this would actually form the basis of our Pentagonal rules subdivision. In the case of my script, I've arbitrarily chosen the size of the interior polygon here. That's just given it as a given rule from fractional rule that's given from like the barycentric center of the polygon itself. That barycentric center is actually the centroid of the outer polygon, or the outer pentagon in this case. So, and when we're constructing this, that we see that there are a lot of symmetries given here. Not only do we have a midpoint on the outer polygon that forms the basis of the spokes radiating towards the center of the polygon itself, but that we have an interior polygon that's a pentagon that's set in the subdivision process. For each subdivision level, then it would go on to iterate in the same fashion for each of these given pentagons. We would just repeat the process of noting and having noted, for instance, that from the spokes we have yet another polygon formed, and that's yet another pentagon that's formed on the outside of the interior, between kind of like the interior pentagon that's shown, the smallest pentagon that's shown in the diagram versus the largest. We also have these additional polygons that are kind of wrapped around the interior pentagon. So in the script itself, we would probably note that it's important in tracking, all given in the subdivision method, all given created polygons that are occurring in the process of subdividing it as well. So in tracking these polygons, for instance, we would simply find it's kind of like the closed loop of the polygon, which means that from one given vertex we can wind in one particular direction around the polygon and return back to the same vertex. In this case, I don't have anything in the script that tracks that formally. Rather, it's just kind of embedded into the script, knowing the design of the subdivision process, so that if, for instance, we've created a midpoint subdivision on this outer pentagon for at least like one edge, and a neighboring edge has a midpoint subdivision, we know that there should be at least 3 given vertices that are matched to a given subdivision polygon. So we already have 3 of those vertices. The 2 vertices that are created, which is given on the most interior polygon, that's shown here, the smallest and most interior, which is closest to the barycentric center of the polygon itself, is given literally. In this case, we can use something like polar coordinates and generating those 2 points given some sort of subdivision method. We know that if we take the, for instance, the vector that runs from the barycentric center to the midpoint itself, we have the direction that would lead to one of those interior polygon points that's shown. So in creating the rule and constructing those points, what we would simply need to do is find some sort of common radii that would generate those points for each, going from the center again of the polygon to the midpoint. So we can actually create that. I just use simply a fractional rule, which is if we know the distance that goes from the midpoint to the center, if we know the magnitude of the vector, which is the distance, then we can just subdivide that distance by some given given desired or user specified rule. In this case, I specified it as some fraction of the total distance. I've left it literally as the frac variable declared at the outset of the script program itself. So, for instance, if it was set at 0.5, it would be half the distance from the center of the polygon to the midpoint. So somewhere in that region, it would actually be a little bit greater. In this case, I believe it was somewhere in the 0.3 times the original magnitude that I chose that. So when we have those vectors that tell us the direction from the center to the midpoint, it is extremely useful to us because we can actually normalize those vectors, which, if you know anything about normalization in working with the vector mathematics, normalized vector just means that we just go to it's a distance of 1, which would be on the something on the unit circle. So we can multiply, for instance, any scalar value to it. If we know the original magnitude, which is the distance of the original vector, we can multiply that times the unit vector to reproduce the original vector. Or we can, in the same direction, moving in the same direction as the original vector, or the unit vector, which is a normalized vector of the original vector, we can move to some point along the lines in the direction of the original vector. So it's a nice way in vector math. If you normalize a vector and multiply it by a given scalar, it's a nice way of interpolating on a given line to a given position on that line itself. So in this case, that's exactly what we're doing in determining the points of the polygon, is that we keep it from the center of the polygon. We move in the direction towards the midpoint. For each given side, we have the vectors that move in the original direction, and then we interpolate to a given position that form the basis of the points. And what's nice about this is that the subdivision points that are there are automatically chosen based on the subdivision rule that we set with the midpoint subdivision. So meaning if we had 6 sides, we would a 6-sided polygon originally, which is a hexagon, we would have literally 6 radiating spokes, and thus the interior polygon would be a hexagon and not a pentagon. Or if we had a triangle, we would have the most innermost polygon at the smallest and closest to the barycentric center of the polygon itself would be a triangle. So it, regardless of the subdivision method that we choose, we always produce an innermost polygon that's matched to the outermost polygon itself, even if the rule is still for instance, a pentagonal subdivision rule that we're using in this case. So the other thing, and I presume that most listeners may have some sort of vector algebra experience, but I did want to comment further that the choice of vector math is particularly nice because we can take the vectors themselves independent of their Cartesian coordinate positions, and we can, for instance, determine if we're going from one vector to another, we can use them usefully informing the basis of like not only finding the direction of one point relative to another, but in terms of the metric properties, measuring distance, and then again, as I've stated before, interpolating positions between, say, two position points. And the nice thing with the vector math in this, and we can see this from this diagram, we have the vector shown as B, which you can think of as the position of, say, a point B at the head of the vector itself, at the arrow, tip of the arrow. That's given from, say, a point of origin, while another vector A shows a point A at the tip. If we wanted to know what the position of B were in relation to, say, the coordinate position of, or using the original coordinate position of A, its origin position, we could do so by simply adding these two vectors together. So they show, for instance, the vector A down here in blue, and its vector originates, say, from a coordinate origin. We could think of that as just being 0, 0 on some origin that's defined for the vector A. And then we have B moving in relation to A in the direction of B up to a given endpoint, which is at the tip of the arrow itself of B. And we can see that under the rules of vector addition, A plus B, we have this orange vector, which points from the point of origin of A all the way to the point that B would terminate at under the rules of algebraic rules of vector addition, A plus B. So if we have, that positions defined that are kind of like arbitrary for one coordinate system, say for some position, and we have another position that's defined under a different coordinate system, under a different point of origin, we could see kind of the usefulness in finding, say, a relationship between one point and another, and that's just using vector math. But again, and this is all kind of useful to us because this helps us in terms of being able to define and measure, and in the case of the script that we're using under this finite rules subdivision script that we've constructed a method of decomposing a given polygon and, well, I shouldn't say decomposing it, but subdividing it, using kind of the similar symmetric rule and at each given level and the subdivision level rules that are formed there. So I'm going to actually go ahead and pull up the script and just kind of cover some of the basis of and again, this is kind of a weekend project. I kind of threw all this together, but I did kind of extend off of some ideas that I'd worked on like in previous weekend projects in implementing this subdivision. And this probably also comes from having worked in geometry, especially working with mesh geometry, like topological mesh geometry, working with it enough to where kind of having some sort of basis of, common things that components and things that I typically utilize when constructing the script. So at the outset, I'll kind of cover some of the declared variables. These are some of these, most of them, save one, which is this p-vector array. variable, which is not user adjustable. The rest are pretty much things that you can adjust in the script itself. So this, for instance, this int ngons s1 variable allows you to change the number of sides for the outer polygon that you want to subdivide. So if you wanted, for instance, a pentagon, it's shown here at 5, which means 5 sides. Hexagon would be 6. Octagon would be 8, and so forth. So that can all be adjusted with that variable. And then we have this RNG1. This just simply means the size of the polygon. So it'd be 300 pixels wide, starting from the coordinate origin, which is actually subdivided, or I should say translated. The point of origin has been translated to half the frame at 720p frame width and height. So we would be using this generating polygon using polar coordinates in the circle. So if you know about generating a polygon on a circle itself, if it's the circle of 300 pixels and radii, the points of the polygon would fall on that circle itself, and we just connect the line segments running from one vertex to another, and we use, in this case, to generate the polygon, we use an equal angle subdivision for all points on the polygon. So for instance, the pentagon moving from one vertex to the next, to the next, to the next has the same angle in polar coordinates. The same is true for the triangle or the square or any other generated polygon. So it's pretty simple actually to do that. When you're generating the polygon itself, you're just like dividing by 360 degrees or 2 pi radians. You're dividing by, to generate, say, a square, you're dividing that by 4, and that's the determinate angle. Increment angle that you're using. So you'd start, say, at 0 pi. The simplest starts at 0 pi, which actually generates with the quadrilateral. It'd look something like a diamond, unless you do what I do, which is you start with a given rotational angle so that it looks like a square when it's rendered, in our given view. But so we would divide, say, 360 degrees by 4, and that resultant increment angle would be used as we increment the angle from, say, 0 pi radians. We add that and then keep adding that, and successively, like for 3 times, or actually, let me think about that. Yeah, that would be 3 times to generate all the points, or actually 4 times. I take that back, to generate the points on the square. So that, in essence, is what we're doing when we're using polar coordinates and generating. And that's actually, I think I show that down here in the script and the setup itself. Let me look down here. Yeah, this is at line. Let's get the ngon points. Ngons S1, RNG1, NG1, POS, which is just, you'll notice that when I construct functions here, I never use output, like return outputs. Instead, I use a call by, it's an implicit way of doing it in Java, because in C++ you can do like call by, I believe it's reference, that allows you to write values to a given variable, input variable. to it. In Java, you can't formally declare, and this is like Python, you can't formally declare call by reference, but call by reference can be implicitly used in Java or Python by simply using a given container that allows for writing values into that container. So if you set a value, if you use, for instance, something like an array, or you use a hash map, or you use an array list, which is, you see that quite commonly. I've got arrays, array lists, or I'm actually using a class object or an array list of a class object as a container for storing that data. When you pass that array list of the class object into the function itself, you can actually write those values to that container without having to use any sort of return output to write it. So it's automatically done once you pass the array list, for instance, of the class object into the function, and you set it interior to that function. It's kind of like it's like in essence call by reference in C++, kind of the same deal. It'd almost be like the container having some sort of global scope too. When you're setting it, it's no longer kind of localized to the function itself, but extended outside of the function. Now, if I were to pass, say, just a float object, a float type object to the function itself, and write it interior to a given function with its given scope range, the variable for that float object, type object, would be set to the function itself. So whatever value I set that float to inside of the function would not apply outside of it. So in Java and Python, you do have to have, in order to take advantage of something like call by reference, or something that's similar to it, like as in C++, you have to use a wrapping container to do so, and that's what I've done in virtually all of my function outputs here. So it might seem a bit confusing, although I tend to kind of conform my programming to kind of the conformed rule of using whatever output object, input output object that's being written to. It's usually the last type object in the function itself. So for instance, if we go down to this polar coordinates function, that's polar chord, you'll see a float angle, float radius, and then a p vector xy. Well, the p vector xy is actually the input output variable. So usually I make a habit of whatever input output objects are usually delineated as the last string of objects in the given kind of like a function or method declaration at the outset itself. So if we go down to get ngon points, for instance, p vector array pos is the input output vector, would be kind of like the equivalent of the return p vector array if I had chosen to have that p vector array as a return object instead of using a void on the return. So that is how I typically construct a lot of my functions. The reason for doing that is one nice reason, and I probably should notate and document more closely in the comment line so that people can kind of follow that. But the one particular reason that you might find that useful is that you can have multiple input-output returns without having to lump them in any given one class object as a wrapper and containing all of those return objects that are being modified. It's probably not very good programming practice, and doing that, and especially not leaving it notated. It's probably good to use one type of return input-output return object itself. But nonetheless, that's the one advantage of using something like the equivalent of a call by reference programming that I've seen quite commonly in C and C++, or actually C++ at least. Just going past the user variable declarations here, just getting into the script, I've made use of some interesting, and this is the advantage of using like object-oriented class objects themselves, is that you can define things like that are like unique containers for objects themselves. In this case, I've created a container called class object container called Polygon, which includes the vertices. We can see there's a variable that's declared down there that's a p-vector array, which is kind of like an XYZ vector given from some just standard point of origin for all such polygons. It's kind of assumed there, but we have a p-vector array, which is an array of p-vector vertices, and then we have a p-vector center, which is the barycentric center of the polygon, or the centroid. We can think of it synonymously in those ways. Then we have what I determine as p-vector spokes. I use this array, the spoke array. It's more useful. I decided to do this mostly for animation purposes, because in the animation sequence, before we actually have all the constructed polygons in the subdivision sequence, we have kind of like these spokes radiating out, kind of growing larger and larger until they complete the subdivision cycle to whatever edge that they're going. So I use this variable called spokes, which kind of like characterizes, it's useful for our kind of animation characteristics here. And then we have, it's a float array called spoke scalars, which is just kind of the base increment value that we would use for our animation cycle. The spoke scalar, as we'll see later in the program itself, it's kind of like a unit scale increment that we add when we want to refer to how much we push the spoke itself in a given direction by distance amount. We would add this kind of spokes, or multiply this spoke scalar times the next variable, or the next extracted data, which is the spokes from the spokes norm class. That's the kind of the unit vectors and the direction of the given spoke that we're animating. We would multiply that spoke scalar value times that spokes norm, which would tell us how much we need to, it would tell us how much we're adding in so many words to our given spoke itself, or it would give us a vector, I should say, that would be added to the existing animation spoke. So we have this spokes norm, which is just a unit normal of each given spoke radii or spoke that's being animated in the subdivision sequence. And then we have this next, which is sync vals, which is the actual current spoke increment scalar value. So this is again a float array. That's where all of these spoke data, the scalar data, is stored. If you think about this in the animation cycle, the direction of the spoke itself is not changing. It's always staying the same. So we can always refer to the spoke norm for that given position point if we want to find the direction. To find the distance of the spoke itself, though, we would use the scalar values and multiply it times the spoke norm, which would determine how far that we're radiating outward for each given spoke. So we have yet another variable that I've stored internally on this polygon class, which tells us, okay, we're at this distance right now. We add the spoke scalar to this distance, or this particular S inc val's present scale value, and we just keep adding these increments on each given animation cycle, iteration of the animation cycle. We keep adding this scalar value until we reach the full length subdivision spoke length, and forming the subdivision polygons that we need. So that kind of explains those. We did have one other thing, which are the points originating on the most interior, and I should have stated in the comments, points originating on the smallest interior polygon boundary. For instance, in the diagram that's shown that I showed earlier in that slide, it would be the most interior, for instance, pentagon, the smallest pentagon closest to, whose points are closest to the centroid of that of the total polygon, or the outermost polygon geometry. So we keep track of those interior points. This is kind of useful for animation. That's pre-computation or setup computation purposes, so that we don't have to do it while we're doing compute that information or data while we're doing the animation itself. So we have, let's see, this int poly points as well, which is an array list, p-vector array list. This is just like a p-vector array, except the array list has some unique advantages where you don't have to pre-size your array when you're constructing it. You can just kind of use it as an add needed basis, which is the one reason why I did this is that, for instance, in the case of like the all generating polygons, if we use, say, a triangle and we used pentagonal subdivision, the innermost polygon that would be generated would be a triangle, but additionally we would have pentagon or five-sided polygons, or five n-gons that were generated additionally interior, that are not matched to the three-gon. So we have kind of like we have an array list that of polygons that may not exactly be matched, to a given. Well, it may not be matched for each given subdivision level, is I guess what I'm trying to say here. So because at each iteration cycle, we may have, for instance, on the three-gon, we start with the three-gon and we use pentagonal subdivision on the first iteration level. We'll have an interior triangle, but if we go to each of the the 5 gons that are also set up surrounding the 3 gon, we would have a polygon, instead an interior subdivision of that at the next level that's a 5 gon and not a 3 gon. So we can't always assume that, that we're going to have the same constructive list. So we would have to have some sort of decision criteria or condition statement that actually tests to see what type of interior polygon, P2S polygon, would be generated based on the original polygon subdivision, or the polygon, the number of sides that we're working on the next level of the subdivision cycle. So instead, kind of using the array list gets around all of those problems, because the array list can be sized as necessary based on its input points. So it can be as many points as we want, and we don't have to worry about outset declarations or testing at that. So that's kind of why I had chose to do that, and it was probably the choice of using the original p-vector array was just because I used that at the outset when I was beginning to construct all of these. I probably could have used the array list as well in constructing the vertices, something like an array list p-vector. Unfortunately, the array list does have some differences in terms of accessor methods, namely, if we're wanting to get the size of the array list, we can't use something like dot length of that array list to get it. Instead, we have to use dot size and parentheses, or starting parentheses and close parentheses. You can see that kind of in some of these 4 iterations. It's kind of something very simple like that, alongside of the difference in calling an array value versus with an array list. We typically, or I believe that the call is given by a dot get, and then the value in that array list, the index value in that array list, to access that given object in the array list. Whereas in a given array, we just use like brackets followed by the index to get the value or set it. So it's a little bit different working with array lists. That made me go ahead and stick with the array, as I had already constructed much of my program and hadn't really wanted to go back and rewrite things to make it convenient for the array list itself. I could have probably have used operator or function overloading, method overloading, and then maybe some variable, using something like a variable overloading or something like that to probably solve some of those problems, but I didn't really want to get into it, and just stick with what I've had going there. So just kind of getting into some of the other nuts and bolts of the program itself. Some of them are probably already explained. We have like the get n-gon points, which is getting the n-gon points is simply making use of using some sort of generating circle and an equal angle subdivision for the polygon type that we're wanting to subdivide. And then iterating through all of those angle increments to determine the polygon with its given vertices and neighboring vertices at that for the polygon, usually in one given winding direction. And when I say winding, that just means that we're rotating in uniformly in a given direction. We're not changing directions when we're winding around those vertices on the polygon. Then we have another function down here, which is get n-gon subdivision points. in this case, this is kind of extended from a previous weekend project where I was using Subdivision, like a vector interpolating approach in constructing polygons it was a polygon morphing project, and to do that I had to create kind of an equivalence, almost like an equivalence class from one polygon to the next. I did that by using kind of the least common multiple between the two polygon types in terms of the n number of sides for each of them. So finding the least common multiple would tell us how many vertices would be necessary between the two polygons themselves, how many vertices would be necessary to have them matched in an equivalent way, for vertex to vertex. That isn't to say that the vertices are matched in terms of their positions, but that we just have the same number of vertices, period. So I use this, I just simply adapted from that project to get n-gon subdivision points. I adapted that function or method in this particular script, which was useful in finding the midpoint subdivision on, say, the outer polygon surface. And then I made use of one other formulation. You can find this through Wikipedia sources. I just used the polygon centroid computation by purely iterating through all the vertices and computing their signed area alongside computing their centers based on the given formulation. So this is not mine. This is just, again, Wikipedia source and for the actual math formula itself. And then I have this subdivide. And the way that I decided to go ahead and organize my subdivision, and I was thinking about this when I was constructing this program. I was like, okay, well, I want to have some data already ready to go when I do the animation cycle. I don't want to have to be computing certain things when I'm doing the animation. That would just be kind of wasted computation if I can go ahead and compute ahead, at all given levels, have that kind of information ready to go. All we need to do is just kind of access it on an as needed basis when we do the animation cycle and just compute what we need. I'm not saying I did that perfectly, but I did try to do quite some pre-computation work to kind of handle that before I actually got into animating the subdivision itself. So the one thing that I did make use of was having at each subdivision level, it's structured, well, the way that I have it structured is that we can define all subdivisions as kind of like in a family of polygons. So one subdivision level would have one polygon, obviously the outer polygon, the outermost fivegon in the diagram that we showed. And then another subdivision level, the next subdivision level would be represented by all of the interior polygons that were subdivided and created in that given subdivision sequence. So in the case of the Pentagon, kind of going back to the slide here, we would have a new we would add to that family a new set of polygons that would look like, well, we have in this slide, I'm just going back to the slide animation here, we would have this 12 o'clock pentagon. It's kind of one of the larger interior polygons that's shown in the slide, and then moving down to just to the right, we have another polygon, and then we have another polygon. If we're just winding around these interior polygons kind of in a given clockwise direction. We had like 1, 2, 3, 4, 5 polygons that are wrapped around this most interior, smallest pentagon, and then we would construct, maybe in the script, that interior polygon as well. And so that would be added to that like a polygon in array list, and then that in turn, the polys array list would be passed to the P family, representing another subdivision level. So the way that we do this is that so that when I'm doing the animation sequence, all I have to do is refer to a given subdivision level. I can refer to this this double array list, which is a polygon, or it's a double polygon array list, kind of a two-dimensional polygon array list. I can refer to the desired level in determining the animations, all the animation sequences that I need to do. So if I've computed the for the given subdivision level, if I've computed the not only the interior polygon, I can render that for that existing polygon at that subdivision level, but I can also render the animation for the spokes for each of the polygons at that given subdivision level. So the data is already kind of laid out in the script, even before we actually get into the draw animation sequence. That's kind of preloaded in the sequence itself. So, and I'm going to go ahead and pull this back up here in a little bit. Let's see. So let's see that with the script, just going down here, scrolling, and we have the subdivide, which makes use of this, again, this P double or two-dimensional polygon array list, type array list. And then we have this A time, the animation time. That's kind of the variable that I declared at the outset of the script, and then this fractional, which is our frac variable, which is used in determining kind of the size relationship of the most smallest interior polygon relative to the outermost polygon, in terms of sizing relationship. So in the animation cycle, as you can see, it's quite simple in the subdivision level. When we do an iterative call, I'm just simply accessing the last subdivision level with this pfam size -1 call. So whatever the last whatever last level was computed is just recalled in computing the next subdivision level in the method call here. So, and then we have this npolys, which is just a new array list, polygon array list that's given for the new polygon subdivision level, and that's where we store all of our new polygon data. So as we compute the new data at the given subdivision level that we're at, or the given level that we're at in the PFAM class, the last PFAM level, we simply iterate through all of the polygons, grab their vertices, grab their centers, and then we go through the process of subdividing them with a midpoint subdivision rule. This is just given by double the number of existing vertices that we have with a midpoint rule. And then we get the n-gon subdivision points using it's a double subdivision, or we divide each of the vectors moving from one vertex to the next, we divide that distance magnitude by divide it in half, and that determines where the midpoints are in that get n-gon subdivision points function call. And those are stored in that subd-verts, that's p vector array. So as we do that, and then I've declared this, I think it's array list, p vector array list. We have the interior poly points that's stored in an array list format. I decided to do that because, again, it's most convenient doing that because not all interior polygons are the same. Some might be some three-sided, six-sided, or relative to the at least at the first subdivision level, we would have one that's matched according to the outer polygon itself, even using the Pentagonal subdivision rule. Now all other interior polygons, again, they're going to be a five gons, but we would have at least one that is matched according to the original polygon that we're subdividing in terms of the number of sides. So we then go through the process of iterating through the subdivision vertices, and in constructing all of the new polygons that would be created. So in that we have it's a previous vertex, a neighboring, and the next vertex, and then the current vertex. Now the key with this is that, and if we refer to that original slide that showed the Pentagon being subdivided, we have, for instance, at the crown of the Pentagon itself, that's at the highest point of the Pentagon, that might represent the center vertex, and then the next vertex would be just moving in the clockwise direction, approximately like I believe 2 o'clock or 1:30 or somewhere in that range. And if we move counterclockwise from the current vertex, then we would have the previous vertex, and so we would have 3 of those vertexes for at least one subdividing polygon, interior subdividing polygon, but we also have to construct the other 2 points, which are given on the closest to the center of the largest polygon that we're in the process of subdividing. So to do that, I kind of explain. I'm not going to re-explain the process of computing those points, but again, we use that kind of polar coordinates type method in generating those coordinate positions, moving to their midpoint centers from the center of the polygon itself. So when we're winding around all of those outer polygon points, including their midpoint subdivision, or those midpoints, we want to skip over the midpoints and make sure that we're landing on the original polygon points and not the subdivision points. So that's why, for instance, going in the iteration loop itself, when we're iterating over the subdivision points, I have a j plus equal 2 as the increment. So we're always iterating to the next original non-subdivided point on the polygon itself to determine the next interior polygon. And once we've done this process, we've generated all of the innermost interior polygon points, that's the ones that are, again, remember that when I showed in the diagram, you have the smallest possible pentagon closest to the center. As we're doing the process of building up all of these interior polygons that are wrapped around that innermost polygon, we've actually generated the points of that interior polygon, and so that's actually being tracked as we're generating those points. And I just make the call. It's at line 159, and it's at the INT poly, interior poly, and I just have the dot add P1. So we're just adding those, adding that point just once, not to avoid any sort of repetition as we're going through all of those points, all those generating points. So once we have that tracked, we can go ahead and commence the process of and that's shown later. Not only do we add at the end of this kind of subdivision points iteration, do we add the existing polygon that we generated. And by the way, we computed the centroid of that generating polygon so that we could store it in that new polygon. And that's just, you can see that I use the new polygon, and that's just calling the in the class, it's the method, the constructor method there for the polygon class. So we have the new poly, we store that in the npoly's array list, which is the polygons array list that we had. And then we want to make sure that we add finally that innermost polygon after we've iterated through all the subdivision points on the polygon itself. And so that is just simply being written to the, it's being converted from an array list to a p-vector list. And that's, again, for the purposes of adding it to, let me see here. Oh yeah, that's to make sure that we have that interior polygon, have it in a p-vector array or p-vector array for the new polygon constructor method itself, since I don't have a constructor call for like a vertices array list. It's just a p-vector array. So we go about adding that innermost polygon. That's with the line 172 call, npoly's add npoly. It's just the last polygon to add in the subdivision method. And then we go through the process of doing some additional computation work, which is determining at the existing level, not at the new level that we're computing, but at the existing level, computing what the spoke animation spoke data would look like. And that's using, in the subdivision level, we use all the data that we computed. For the next level, we use that to compute what the spoke animation spoke data would look like at the existing level. So when we're doing animation itself, we're actually recalling recalling at the existing level, not at the next level. We're recalling that information, animation sequence or cycle information, and determining how we're going to animate these spokes. So hopefully that's not too confusing there, but the idea is that when we're iterating at a given subdivision level, we're starting at like in the two-dimensional polygon list. If we're recalling at the outermost level, which is the base pentagon, and that's prior to any sort of subdivision, we would have that spoke data already stored at that level, and we would just recall that when we're doing the animation cycle, because that's already that's again provisioned at that level. So when we actually go to the next level, we're actually animating for the next level ahead of that. So in the animation cycle for the existing polygon family class, we're always animating one level ahead using that spoke data information. So if that makes any sense, hopefully, to the listener there. So I'm not going to get into exactly what I did in computing the spoke data, since I kind of already explained that earlier in the video of kind of what's going on there. But it's all done here. There is one additional thing, though, that I would comment on that. The spoke animation cycle, as I stated before, when we're animating, the direction of the lines themselves, the spokes that are radiating outward, the direction does not change. So we're actually only interested in the scalar of the vectors themselves that determine the actual distance terminus on the line, the spoke line itself. So in the animation cycle, it is I do make use of this A time, which is the amount of time at 60 frames per second. So we're converting that from seconds, animation time seconds, to just total, or I should say increment scale per frame. So that's kind of the conversion factor here, and that's noted in the MP12, which is just a scalar float value. And that's being stored, that increment value is being stored in the actual polygon. Again, that's at the current polygon level, not the next polygon level when we're computing that data. And then we're also storing, again, the norm, the unit normal, that's the direction of the spoke itself. So going down a little bit further, I think some of these may be a little more self-explanatory if you have any knowledge of processing. Part of it is if you know anything about P-shapes, the P-shape class, you use something like the function call begin shape to start the shape, and then you add the vertices, and then you end the shape, and prior to that, add stroke weight, or no fill data, or fill data, whatever that's relevant to the polygon itself. I have this function overloaded with two different input types. So one is a p-vector array, and the other I kept as an array list, since overloading is real simple to do in this case, and it's worthwhile since I don't have to make the call in converting from say an array list, a p-vector array list, to a p-vector array, and doing that so I can use either possible input to compute an n-gon that would be used for shape rendering, or for an output p shape to be rendered. So the things that are rendered, and this getting into the draw animation cycle, since I've explained a lot of this, what's going on in the pre-computation stage, I'll just kind of go down to the draw stage. You can kind of get a sense in the setup of what I was doing. I have a user-specified subdiv level. We just iterate subdivision levels by repeatedly calling the subdivide and inputting the P family class. I did kind of accept myself on the convention of having an input-output object at the on the method call at the beginning of, or at the start of the variables list as opposed to the end. Probably could have changed that for ordering's sake, but the P family class is what is being inputted and output written to. So again, all of the functions have void returns, so we don't have to worry about any sort of return handling on the method call itself. So that again, if that is handled in the setup, that's prior to any sort of draw frame animation. Now, I did use a number of Boolean kind of variables. These are kind of outset declarations, kind of given more global to the scope that are used in the draw animation sequencing. One control variable is called next level, that just indicates when we move to iterate to the next level in the draw animation cycle. Continue animation just means whether or not we're going to continue animating anything, like in terms of like spoke animation. And then record shapes is when we have new polygon shapes to add. Most of these record shapes, by the way, are the innermost polygons. They're not it's the innermost polygon on the subdivision on the so for instance, with the 5-gon subdivision, we would have the smallest pentagon that would be iterated on each cycle level. You can actually, when you run the script, you can see the effect of that, because you see these little pentagons, interior pentagons with spokes radiating outward from that. So that data is actually recorded under the record shapes. That smallest pentagon is actually recorded using this this Boolean control variable that tells us, okay, when we start the next level and we have this condition that's true, we want to flag record shapes as true, and we'll go ahead and add this shape, add these shapes, to be rendered on each frame. And then we have C level, which represents the current level that we're working at when we're doing the animation drawing. And then we have max scaler. I don't know if this is technically being used alongside P scaler. I was thinking in one direction, and then I think I ended up not really using that because it wasn't necessary. And then we have array list polys, and then it's kind of interesting, a P vector array list, which is kind of like a two-dimensional. It might be normally a two-dimensional array list, but in this case, I chose to have an outer array list and an interior P vector array that's used as a line list, and that's for the frame, the spoke animation. Or I take that back. That is no, that actually is because I don't actually render. I render lines for the only thing that I actually render in terms of P shapes are the smallest interior polygons, and the at the outset, the level 0 of the original polygon itself prior to any subdivision, that's being rendered as a P shape. So the rest of the rendering that's going on here is given by lines, purely by lines alone, and not shapes. And I think the reason why I did that was to avoid animation redundancy in terms of like the P shapes having overlapping lines or something like that, so that we only have one line that's rendered. So it gives technically I'm not rendering distinct P shapes. So if you were writing this to do like fill color data, it might be necessary to convert to a system where you were rendering P shapes alone that you could fill with color data, as opposed to working with the final or working with these lines, which is what I instead chose to do to kind of, I was thinking maybe this would save me a little bit of graphical computational overhead, again, with like overlapping lines that would be rendered if I chose to render distinct P shapes for each of the interior polygons, other interior polygons that are shown. So, getting to the actual animation cycle. So, the idea is that sequentially we start with the background being dark. We translate to a common point of origin for all polygon rendering, and that starts at half the width and half of the length of the given screen size itself for the common origin, point of origin. And then we go about the process of rendering the outermost polygon shape. In the case of the diagram, it's the outermost or the largest pentagon that's shown. And then we go through the process. If we have any lines that need to be rendered, these are non-animated in the context of that spoke model that I described earlier. These are just lines that are already completed. Those would be rendered as they've been stored. And then we go to this if continue animation condition. So if we have things to animate, then that being true, we go through grabbing at the current level, animation level. We grab the set of polygons that we need to animate on, and we grab all that data, that spoke data that we need, and then we start rendering it. I'm not going to get into the specifics of the animation cycle other than to say that it's like 275. Line 275 is where we actually increment the scalar of the spoke itself for each polygon, each given spoke. So we're kind of iterating through each of those spokes, and that should be evident here. It's SPS scalars. That's basically the spoke scalars. That's their base. I think it's polygon sync vals is the actual stored present scalar value. So we do have a control condition that tells us when to record the new interior polygon shapes. That's set that the poly.sync vals j is equal to 0. That just simply means that when the spokes are when we start the new level of frame animation, subdivision frame animation, we have all the radiating spokes are at a 0 distance. So we're just starting that cycle. So we want to record all of the little interior fivegons that are generally popping up at that subdivision level, aside from so once we record those polygons, and I'm trying to look here to see what I was doing. The polygon sync vals j. Oh, that's just recording the total. Oh, that's grabbing the that's just grabbing the start data for the spokes. I probably didn't need to do this this way. I found out that when I was animating, I decided to go with this P2S, which is the polygon. Actually, that's where I do add the interior polygon shape, is at the P2S. at that particular point. It seems like a bit of a redundancy here, but I probably have to go back and check on that code. But in any event, it all works. But we ended up flagging this record shapes, which is done later, where we actually record from I believe the P2S. We create the ngon from the polygon P2S class itself, and that's, again, if we recall from the create ngon, I have that overloaded to accept that p-vector array list class to do that. So the record shapes, you can see that down at starting at 287 under that conditional statement, and you'll notice that is also outside of iterating this after we've completed iterating on the spokes themselves, but we're still inside the iteration of the polygon itself. So we still have the original polygon referred to when we're recording that shape. So it's kind of a unique situation when we're actually recording the shape. It should be kind of like it's only done once on one given frame per polygon at a given level, any given level that we make that call. So, and some of the other things that are done here, we have the line animation sequence, which just refers to grabbing all of that data from the polygon and finding out what it's starting versus I should say starting position, which is the polygon P2S get J dot X, since the P2S get J refers to a P vector, we can refer to the X coordinate data off of that with the dot X call, and the same is true with the polygon P2S get J dot Y, and getting the Y coordinate data. That's just the originating point of the line on the spoke, and then it goes to the P1 dot X, P1 dot Y on the animation cycle, grabbing that spokes norm and grabbing the async vals data, which is the scalar data, which is existing stored animation scalar. And then we just stroke the line with the color, which is in this case white, 255 value. Stroke weight is just the line weight. I indicated 0.5 here. You could potentially adjust that up and down. I didn't leave it user specified in terms of possible weighting, but you can adjust that alongside the line color data as well if you wanted to do that. So going down below a little further below the record shape, since I've already explained that, we have the next level iteration. That's when we reach the max condition, and I should go up here. I believe there's a condition. It's shown on line 276 that explains excuse me there, when we would go to the next animation or next subdivision level in animating, and that condition is when the scalar lengths or the scalar distance is greater than the total possible animation scale distance. It should represent the total distance from, let's say, the centroid of the polygon itself to the midpoint. So when it gets greater than or equal to that distance, then we go ahead and flag the animation level or say we need to go to the next level and stop animation at the existing level. So then we move to the next level, and that's shown starting at 297, and we go through the process of getting that polygon data, setting it at the polygon variable level, and I apologize, at the existing polygon level, what we end up doing is just getting the line list at the existing level of all completed lines. Those are all of the spokes that are completed. We add that to the line list so that when we go through the next level, animation level, we're just re-rendering all of those completed lines, spoke lines that would represent the new interior polygons. And we also make sure to iterate our C-level variable, and we also check to see if we've reached the end of our animation sequence, which is actually in the P-family class. It is at not the last array list element, but it's at the previous array list element, because if you remember in the animation, spoke animation, we're actually iterating the next level on the existing level that we're at. So we complete it actually when we're at the previous to the last index. That's when the animation stops, once we get past that point, I believe, there. So that's kind of how that works. And then we also flag next level as false so that we don't repeatedly go over this, since we've done all the work that we need to do in setting up, getting to the next animation. Subdivision animation. Okay, well, that kind of completes, hopefully it provides you with the further information on this Pentagonal rule subdivision, how it's all being worked here. There's a lot of information here, but hopefully that kind of gives you an idea of what's going on. I did want to thank you for listening in, and you have a good day there.